It is the largest, most complex machine ever created by mankind, a silent network of energy spanning continents. This is the electrical power grid. The grid's fundamental mission is simple: keep supply perfectly matched to demand, instantly, across vast distances. Our journey begins at the source, the power plant. Whether fueled by steam, water, or wind, energy is first converted into mechanical rotation. The heart of generation is the alternator. This machine converts the mechanical rotation into alternating current AC, following Faraday's law. The frequency of this AC output, 50 or 60 Hertz, must be synchronized and perfectly stable across the entire grid system. The initial voltage produced by the generator is typically moderate, 13 to 25 kilovolts. This is not enough for long-distance travel. The immediate problem is line loss. Transmitting power at low voltage results in massive energy waste as heat, crippling the system's efficiency. The engineering solution: transmit at extremely high voltage, drastically lowering the current. This relies on the step-up transformer. The transformer boosts the voltage from 25 kilovolts to extreme levels up to 500 kilovolts. This is the first, most crucial transformation. Once the power is stepped up, it leaves the plant and enters the transmission system, the network, designed for maximum distance and minimum loss. The high-voltage lines are often bare conductors, suspended by massive insulators that prevent the extreme voltage from arcing to the grounded tower. Even with high-voltage lines face resistance, series capacitors and shunt reactors are strategically placed to condition the power and minimize reactive losses. The grid uses multiple parallel lines for redundancy and reliability. If one line fails, power is automatically rerouted through others. Despite the dominance of AC, some ultra-long distance links, especially undersea, use HVDC, high-voltage DC transmission. This is because DC eliminates AC's reactive losses and is more efficient over very long distances, although it requires complex conversion stations. The converter stations on both ends of the HVDC link use powerful thyristors to switch between AC and DC, bridging the two systems. This entire massive transmission system operates under the principle of N1 reliability. The grid must withstand the loss of its single largest component without collapse. The seamless operation of this system is critical. A failure to synchronize frequency or manage voltage can lead to a cascading failure, massive blackout. After traveling vast distances, the power reaches a major substation. This is the traffic control hub of the electrical world. The first step at the substation is to reduce the transmission voltage from 500 kilovolts down to around 138 kilovolts to prepare the power for regional distribution. Substations are filled with critical protection equipment, most notably high-voltage circuit breakers designed to isolate faults instantly. These specialized breakers use compressed gas or oil to rapidly extinguish the violent electrical arc formed when interrupting massive fault currents. Disconnect switches are used for maintenance. These manually operated switches isolate equipment, ensuring worker safety during repair or testing. Bus bars are the collection points within the substation. massive conductors that distribute power to different circuits, leaving the station. Current transformers (CTs) and potential transformers (PTs) monitor the grid, providing precise, scaled-down measurements to the protection relays. The protection relays are the brains of the substation. They instantly detect anomalies like overcurrent, undervoltage, or phase imbalance. When a fault is detected, the relay commands the appropriate circuit breaker to open, isolating the problem area in milliseconds to prevent widespread damage. The power now flows into the distribution system. This network takes the regional voltage 13 kilovolts to 35 kilovolts and delivers it to local neighborhoods. This is the radial system, where power flows outward from substations into a tree-like structure, serving thousands of local customers. At the street level, the distribution transformer performs the final critical step-down from high distribution voltage, for example, 13 kilovolts, to low service voltage, for example, 240 volts. Inside, this final step-down is achieved with the highest turn ratio difference, ensuring the power is safe and ready for household consumption. From the pole, power is split into individual services. Homes typically receive single-phase power, while businesses receive three-phase power. The entire distribution system is now monitored by smart meters, the digital sensors that provide real-time consumption and grid health data. This two-way data flow allows the utility to instantly detect local faults, balance neighborhood load, and respond to outages with pinpoint accuracy. Reclosers are automatic circuit breakers on the distribution lines that attempt to restore power after a temporary fault, like a tree branch hitting a line. If the fault persists, the recloser locks out, permanently isolating the section to protect the grid from continuous damage. This system of segmented protection ensures that only a small portion of the grid is affected by local faults, limiting disruption. The efficiency of the entire grid is constantly analyzed, focusing on reducing non-technical losses such as energy theft and metering errors. The greatest challenge is stability. The grid must ensure that the total power supplied precisely equals the total power consumed at all times. Any mismatch causes the system frequency to fluctuate too much. Supply increases frequency, too little decreases it. Primary frequency control is instantaneous. Generators quickly and automatically adjust their mechanical input to correct minor frequency deviations. Secondary control is handled centrally. A sophisticated control center constantly monitors the grid's area control error (ACE). The control center sends automatic generation control (AGC) signals to power plants, instructing them to slowly ramp up or ramp down their output. The second major stability factor is voltage. While frequency is universal, voltage must be maintained locally, usually within a 5% tolerance. Reactive power (VARs) manages voltage. Transformers use on-load tap changes OLTC to adjust the turns ratio, fine-tuning the voltage output. Additionally, large capacitors and reactors static VAR compensators are switched in and out of the line to either increase or decrease local reactive power. This constant dance between active power watts and reactive power VARs ensures both the frequency and the local voltage remain stable. The greatest threat to stability is the cascading failure. A single fault can rapidly escalate due to protective relays overreacting to the initial voltage dip. To counteract this, the grid utilizes Synchrophaser's high-speed GPS-synchronized devices that provide extremely accurate wide-area measurements. If a collapse is unavoidable, load shedding occurs. The control center deliberately disconnects non-critical areas to save the rest of the grid. Islanding is another defense, isolating a section of the grid that still has adequate generation to run independently until repairs are made. The future of the grid is the smart grid. This relies on the bidirectional communication of devices like the smart meter and VFD. The smart grid allows for better integration of renewable energy sources like solar and wind, which are inherently intermittent, unpredictable. The unpredictability of renewables is balanced by large-scale battery storage. These units can instantly inject or absorb power, stabilizing the grid frequency. Looking forward, the grid must handle increased demand from electric vehicles. This requires strategic planning to prevent local transformer overloads. Vehicle 2-grid V2G technology may turn EVs into mobile batteries, allowing them to feed power back into the grid during peak demand. The operation of the grid is a monumental, continuous achievement, involving billions of components working together in perfect synchronization. It is the essential engine of modern civilization, making complex energy transfer look deceptively simple. We have analyzed the 4 essential stages: generation, step-up, transmission, step-down substation, and local distribution. But the true complexity lies in the protection hierarchy. Every failure is detected and contained by layers of intelligent relay systems. The synchronized frequency is the single most sensitive factor. Even a small deviation can cause massive mechanical and electrical stress on large turbines. The future demands not just reliability, but resilience, the grid's ability to quickly recover from natural disasters, physical attacks, and cyber threats. Cybersecurity is now paramount. The control systems, communications networks, and smart meters must be shielded from unauthorized digital access.
In essence, the power grid is a living, breathing machine that never rests. It is a constant miracle of balancing supply, demand, and physical constraints.
The seamless power you receive is the result of thousands of continuous automated decisions made every second by protective relays and central controllers. The reliance on AC voltage transformation remains the cornerstone. Without the transformer, the entire concept of long-distance electricity is impossible. The eventual widespread adoption of HVDC for global interconnectivity will further increase efficiency, bridging distant renewable energy sources to population centers. But even in a future DC world, the final local step-down to safe household voltage will still rely on simplified conversion electronics. This constant evolution, driven by the need for efficiency and reliability, keeps our civilization running, safe from the chaotic forces of raw nature. We hope this comprehensive look into the complex world of the electrical power grid has enhanced your understanding of the energy that powers your life. If you were impressed by the monumental scale and technical sophistication of this system, please consider supporting UA Electric.